Good afternoon, everybody. I am going to talk about the circuit-style segment routing. Yesterday, actually, Christian introduced the circuit-style segment routing in the context of private line emulation. I'm going to take that to another domain. That's basically the metro networks and circuit-style services there. And if you want to know what they are, actually, they were actually in the Krati's presentation. He had these dotted lines between the CE and the PE, and he was able to reroute that. These are the kind of the services that I want to now move to segment routing. But before I go there, let's take a look at the metro network, a typical metro network. And usually in the metro networks, we have lots of rings. It's very typical for a service provider to have 30, 40, 50 rings in the network. There is a core of the metro network. And this core may be a little bit more meshy than the other rings, but underlying DWDM topology might as well be also a ring itself. But based on the traffic demand, we have express routes, crisscrossing across these maps. And it is not unusual for these rings to be really large, like 10 hops and so forth, because they are going after cell tower, connecting them to each other, to some enterprise sites and so forth, and then coming back and joining to this central ring. And sometimes you may even have smaller rings coming out of these second-level rings and so forth. So what are the requirements for segment-style segment routing? Number one is explicit bandwidth management. In Kriti's example, he had 10 gigabits between CE and the PE, and that is 10 gigabits. Under congestion, it is not 6 gigabits. It's always 10 gigabits. You have to actually enforce that, and only way you do that is basically with bandwidth reservation. The second constraint is if I'm going from A end to the Z end, I need to have diverse path between these two locations, and they need to be node, link, as well as the optical SRLG diverse. The details of the intent. This slide actually explains the intent. Number one, as I mentioned, is the explicit bandwidth management. Because we are doing explicit bandwidth management with segment routing, that means we must have a PCE, because there is no other control plane in the segment routing ecosystem that can actually do bandwidth management. In addition, explicit bandwidth management means even under failures, I don't want to move this traffic to some other link. For example, if you have TI-LFA, you do not want the TI-LFA protection, because when you move that traffic to the TI-LFA protected path, you may be impacting somebody else's PEC connections, which is also supposed to be tagging under all conditions. You want basically traffic switching to happen at the head end. You want to go from primary to the secondary. Second constraint, as I mentioned, is the diversity. And we want the switch over to happen at the head end. And you can do that simply by running SPFD. When you detect the failure in the SPFD, you switch to the other path. We want this to be self-healing against the failures and repairs, or maybe delay changes in the network and so forth. You may want it to move around. And some service providers have additional constraints. For example, some of them would like this forward and the reverse path to be co-routed, but we are seeing less and less of that. It's not as bad as the MPLS-TP days, where people were saying, oh, they have to be exactly co-routed and so forth. And sometimes we hear of the tertiary paths. If the primary fails, create a tertiary. And now that tertiary has to be diverse to the secondary. If secondary fails, create a tertiary, but it needs to be actually diverse to the primary. So there are some additional requirements and so forth, but this is basically the intent that we need to implement with segment routing. To do that, number one is basically we have to deal with the SRLG propagation. We need to basically know the resilience SRLG values at the IP layer. And for that, you need to basically understand the IP links, underlying SNC, the photonics, and so forth. And then you can now carry them up towards the IP network. And then at the IP layer, now you know the SRLG values. Then you can actually compute diverse paths. In addition, there may be optical protection in this network. And then if there's optical protection in the core, maybe you do not need the IP protection in the core section of the metro. You can basically a little bit maybe relax on when you're trying to compute diverse paths at the IP. Maybe you don't need it as much in the core network, but you have to understand these different protections and resiliency in the multiple layers of the network and be able to make decisions based on that. Once you have all of this data, actual path computation itself is actually a piece of cake. We've been doing this for a while. And basically, you go from A end to the Z end. It's diverse. Actually, that should have been another graph. Oh, there it is. And you go from the A end to the Z end. It needs to be diverse, and you select the diverse node, link, SRLG, and all of these diversities, and then you give the bandwidth constraints, and we compute this. And this global CSPF does this beautifully. It's nothing new. We've been doing this for years. But next step is, because we are using segment routing, we need to compress this path in terms of segments, and then program the head-end device to use this SR policy. And for that, we usually typically use PSAB or netconfig and so forth. This approach sounds extremely simple, and it works well until it doesn't. It doesn't work when you have failures and repairs in the network. And the reason for that is illustrated by this example. So we have a path, A, B, E, Z. That's our intended path here. And then I need to compress this as segments. I can actually say my segments are B, E, and Z, because my shortest to B, and then from B to E is going to be this, and then E to Z is going to be that, right? And so forth. This will be my intent. This will be the compressed SID list for that. So if this link was to fail, if I still keep the same B, E, Z, initially there will be a failure. But after the IGP converges, this BEZ is operationally up. Unfortunately, it's now encoding a different path, A, C, D, B, D, E, Z, because it's still this segment list, basically, to go to A to B, the shortest path is that through that ring. And then, you're going to actually take that path. And we do not want this path, because we did not reserve bandwidth on this path. So how do we solve this problem? I mean, the most naive approach is, hey, let the PCE fix it. But if you think about how the convergence happens in the network, first ISAS converges. Then afterwards, there is BGPLS. And sometimes, actually, between ISAS and BGPLS, there may be like a 10-second delay. And eventually, the SDM controller will learn about this. And then now, yeah, it can go and then remove this candidate path. But during this 10 seconds or whatever, basically, the network is sending traffic in the wrong path and without the intention. So how do you solve this problem? The same issue happens with the TLFA protection as well, but I'm not going to go there. But you can ask me after the talk how we solve that problem. What is more surprising, the same issue can also happen with link repairs. Without a failure, this path, this BEZ, may encode a different path in the network. Like, imagine there is a downlink between B and E. It's down currently. So BEZ is encoding A, B, D, E, Z. But when that link comes up, this BEZ path will use A, B, E, Z. It will actually bypass the D. And it's, again, going to use resources on that link, which we did not reserve. I'm not going to go into that detail of that either, in the interest of time. But the trick is, when we compress, we are not just looking at uplinks. We are also looking at downlinks, making sure this compressed SID list actually works under both conditions. There is a proposal at IETF to solve this exact problem. Actually, it's actually a really beautiful solution. I think it's one of those like set it and forget it kind of solutions that I like. And it basically says, do not use segment compression, just use adjacency SIDs end to end. So if one of the links was to go down, you are forced to fail that SR policy. There is no convergence path. After IGP convergence, basically there is no path. The problem is that if you encode in a metro network with all of these rings, especially big rings, if you encode end-to-end the path using adjacency SIDs, that can be very large. It's not unusual for one of these rings to have 10 routers and going across 3 rings to get to the destination. And commercial off-the-shelf component routers, disaggregated routers, we all love low-cost routers, basically cannot handle that. As a matter of fact, if you get near 30, even the other routers, the merchant routers, cannot handle that kind of depth as well. So we cannot really use the IETF solution unmodified in the metro networks. Another work from IETF that got a lot of attention lately and has been discussed in this conference many times is flexible algorithm, or Flex-algo. Nice thing about Flex-algo, it can compress regardless of the length of the path. As long as you can state your requirements as an algorithm in Flex-algo, you will end up having a single SID. That's beautiful in terms of compression, but the problem with the Flex-algo to have these constraints, first, it cannot do bandwidth reservation. Second, it has a diversity model, but it cannot really truly do an SRLG diverse model. So as a result, it's not really suitable for us. But I'm going to use Flex-algo in some other creative way in a second. So for that, we proposed, actually not necessarily proposed, we actually deployed, and it's actually been running on the service provider networks, two solutions. The first one is a general self-healing solution. It uses the PCE. It uses the rules engine in the PCE so that service provider can customize it. Do you just want to bring it up, or do you just want to have a tertiary path signal and so forth? Do you want the human to interfere, or you want actually machine to correct the self-healing behavior? Second solution extends the IETF work. It actually combines both the PCE-based path computation with the Flex-algo-based SID compression. We basically decouple the two problems. Path computation, use PCE. Segment compression, use Flex-algo. And then that also has the same flavor as the IETF's set it and forget it approach. And you can also combine both of them. Then you have the best of both worlds, basically. So how do we do that? So in the segment SR policy, we introduce a new flag called eligible. And when the eligible is set, when the candidate paths are eligible, it's the same segment routing behavior that we all know. The first candidate path that is available is picked by the head-end router, and that's going to be used in the network. So when the link fails, as I said, we can't really rely on the PCE to fix it. Head-end has to react, because head-end is there. Even before the IGP converges, head-end can do something. So head-end is actually already doing BFD and knows this path is down. When the path goes down in the head-end router, it will reset the eligible path to be ineligible or ineligible. And then when that happens, so the path is this long path now, but it's ineligible, and head-end will never switch to it after IGP convergence. So as a result, the candidate path, CFC, the second candidate path, the backup path, will be used until somebody resets this flag. We will never switch to it, even though IGP has converged. That's the small role of a single, small flag, but that gives us the protection when the failure happens. So who is going to correct this flag? So eventually, this link will come up. When it comes up, we want somebody to go and then change this ineligible to eligible. But bad news, we need to react fast. That's the 101 in routing. Good news, you have time. Take your time, right? I mean, you want to avoid the flaps in the network. Bad news, you have to react. Good news, you have to wait. And if it happens again, wait longer, exponential backoff, right? That's the techniques in the routing that we always employ. And then in the case of the good news, basically when this link comes up, PCE looks at it and says, hey, this BEZ now is again encoding my intended path, and then goes and makes it eligible. And that's the first approach. Second approach basically combines the PCE as well as the Flex-algo. The path is computed solely using the PCE. Centralized PCE is not different than what I described so far. But when it's time to compress the SID list, we use flexible algorithm. And for each ring, we employ two algorithms. One algorithm computes paths in the forward direction. The other algorithm computes paths in the reverse direction. So from any node on the ring to any other node on the ring, I have two SIDs. One takes me clockwise, the other one takes me counterclockwise. I'll put that together. It will be a little bit more clear in a second. But how do I do that? Using flexible algorithm. So I color the links in the forward direction. Remember, IP is unidirectional links. I color the links in the forward direction as blue, and the reverse direction is green. In my algorithm 1, I say, clockwise algorithm, I say, take the blue links, avoid the green links. So any path the flexible algorithm clockwise will compute will be forward in this ring. It's going to be clockwise. In the algorithm 2, I'll say, take the green links, but avoid the blue links. So any path, any set that the second algorithm computes will be counterclockwise. So basically, with using a one set, I can cross that link to any node I like, either in the forward direction or in the reverse direction. I don't have to enumerate hop by hop every single adjacency set. And if I'm going across three rings, my PCE knows the intent, computes two paths. He doesn't pay attention to Flex-algo at all. It just computes, uses the topology from BGPLS of these 3 IGP areas, puts them together, and computes a path that has the bandwidth and the diversity requirements. It computes the green path, it computes the brown path. Then in the second phase, PCE says, hey, I am in a ring, and green goes clockwise. So what is the label or the set for node B that will take me there? And let's assume like for B, there is B1, which is clockwise, B2, that's counterclockwise. Basically, for any node, if I say 1, it is clockwise. If I say 2, it is counterclockwise. So to encode the green path, I just need to say B1, clockwise, D1, clockwise, and Z1, clockwise. So I can cross all of these hubs using just 3 sets. Instead of, if I did use the adjacency sets, I think it's 11 hubs there. It would be 11 adjacency sets, which the most hardware cannot do. And whereas with this compression, I can actually do 3, and it has the same benefit as the IETF proposal. For the brown, I am going counterclockwise. So for C, I won't say C1, because if I say C1, I'll actually go clockwise. I'll say C2, so I'll go counterclockwise. Then I'll basically say, hey, the backup is C2, E2, Z2, counterclockwise, counterclockwise, counterclockwise. And then basically with 3 sets, I can go from anywhere in this 3-ring metro to anywhere else. And that compresses it and has the same properties as the IETF proposal. In conclusion, IETF proposal for circuit-style transport service is simple. Unfortunately, if you have metro with the rings and so forth, it's not really suitable for disaggregated CUTS hardware. Actually, I would go ahead and say it's not even suitable for any hardware for that matter. But it's a nice, simple approach because it's a set it and forget it approach. PC doesn't have to react. PC can be disconnected, can be far, can be a data center, whatever. You don't have to deal with these issues. There is another solution using binding sets that you can solve this problem. I don't mind binding sets when you cross area boundaries or the AS boundaries, but just to encode a 20-hop path using 3 binding sets, it's just putting state into the network. The segment routing is supposed to remove from the network. So I'm not really fan of the binding set for these purposes. Anyway, and the second solution in the 2 solutions that we propose, one is the self-healing one with the eligible flag. Second one is the compression. You can combine them. And in our case, because we've been doing this for a while, our customers trust us. Actually, in our deployments, in the first solution, actually people do it self-healing. They don't actually need to have the operator to interact and so forth. But we have a rule engine that can customize the solution, and then you can put have the operator bless this before it is done in the network. And to do this, segment routing SDN controller is key. You have to be multi-layer. You have to understand the optical and IP, the SRLG, and so forth. And then using a rule engine, you can actually, when the failure happens, you can even signal a tertiary path using the same customization the rule engine brings you. Thank you.
Thank you, Nyanjes. Any question? Yes, please.
Yeah, just really quickly, Severin from DOS University. So I have actually a question about the first solution. So you did your example with just a direct link failure at the ingress router. So can you explain how it works if it's an indirect? Because I don't really understand how you switch to the second candidate path without having a non-optimal routing during these types without using microloop avoidance and TLFA.
So both paths, ABEZ and ACFC, is actually pre-provisioned in the head-end router. IGP doesn't have to converge. So those microloops happens when IGP is converging. So these are, think of it like RSPBTE-like paths using SR policy already provisioned at the head-end. Now you run SPFD in both of them. It checks the health of that path. When the link fails, SPFD will fail sub 50 milliseconds. Then it will say, hey, this is ineligible. don't use this, and then the head end will automatically switch to the backup. It's just like a link protection, basically. It
Okay.
will switch to the backup.
But-
But I can describe this a little more detail afterwards if you like. But
Yeah, but just like this, like 50 milliseconds, you have like a non-optimal routing, right? Just like,
no, I am head end. So there is a 50 millisecond outage.
Yeah,
That's
okay.
expected
Yeah.
because there is nothing faster than 50 milliseconds protection
Sure.
in IP networks. During that 50 millisecond, there could be an outage, but within 50 milliseconds, I'll detect it and I will switch. I don't have to converge. I already pre-computed that protection path.
okay, perfect. Yeah, this answers my question. Thank you.
Thank you.
Another question quickly? Yeah.
Yes. Hi, Tengiz.
Hi.
Greg Mirsky, Ericsson.
Hi, Greg.
So, if I understood correctly, so you suggest that the detection takes 50 milliseconds, and then on top of that, there is a switchover time.
No, I mean, the head end is, the incoming interface has two routing table entries, fib entries, I should say. One is taken down, its other one is already there.
Okay.
It's
Yes.
pre-programmed. It's actually, these are not like, it's not like I'm going to the control plane and then changing the
Okay.
candidate path. I already pre-programmed two of them into the fib.
Okay. So, what determines their detection period?
That's actually the service provider's intent to requirements, but typically it is 50 milliseconds, so you have to do your BFD at least 1/3 of that, and then, 3 failures, you declare it down.
In my experience, and basically it was interesting that these time intervals, 50 millisecond switchover goes way back from TDM.
Yeah, absolutely. And these are like TDM-like circuits that become MPLS TP circuits. Now they are becoming segment routing circuit-style circuits.
Right, and actually, if we look closer at it, they had it a little bit differently. So they had 10 millisecond detection time.
Yeah.
So thus, the interval between messages has to run at 3.3 milliseconds. And that's what we can see in Ethernet OEM. And that's what basically same supported in BFD hardware assistance.
Yeah. I mean, I gave the 50 millisecond because it's kind of accepted in the industry. Actually, in the customer deployment, we are indeed doing 3.3 milliseconds BFD Pro.
So actually, you can do even better.
I don't know how much better we can do it, but at the customer deployment, we are doing 3.3 milliseconds, basically a 10-second detection period.
Okay, thank you.
Yeah, thank you, Greg.
Thank you very much. Thank you again, Jajis.